All right, chemists, let's get started. So as you can see, I have the results from recitation 12. What words do we associate with chemistry? Every year it's the same terms come up, you know, chemicals, elements. I'd hope those would come up, but other terms like what's hard, sadness, stress, I think those are valid terms too when thinking about chemistry, but I just want you guys to know that you've come so far. We're almost there, just 2 more days. All of the resources are there for you to study for this exam, so this final exam, so you can find success. So hopefully we'll just have a little bit of fun these last couple days. Chapter 12 is fairly short, no math. Because some of you guys have mentioned you would prefer a conceptual exam over a calculation-based exam. So once we finish chapter 12, I will, I have some of the most incorrect problems from the midterm, the 3 different midterms, and we can go over some of those questions to address some of the misconceptions going into the final exam. So we'll spend some time to do that, and any extra time, you know, today or Wednesday, we'll just continue on with final exam review. So those, there's the results from all of the, you know, different surveys I had you take in recitation. Apparently, you guys prefer conceptual exams and you prefer electrons. Yes. Okay. Additionally, yeah, so it's, you know, what's our favorite E word? All right. If you're taking 1220 with me next year, next term, I asked this similar question, a favorite E word, but instead of enthalpy and electron, I say enthalpy and entropy. So you have a couple months to think about what you're going to say. All right. Additionally, do check your recitation grades because the grade that you see right now in the grade book is what's going to go towards calculating your final letter grade because all of those grades are in, you know, with zeros for your absences and stuff. So do double check that, your final recitation grade. Remember, everyone gets 2 drops. So if you, as long as you have attended 10 out of the 12 recitations, you'll get 100% in that grading category, and you should see that reflected in your Carmen grade book. So those drops are like integrated in there. So if there is a discrepancy, email me as soon as possible because I need to have the grade books finalized by December 11th. So this Sunday at midnight. That means online homework. That's the last day to turn anything in. That includes late assignments, and that includes chapter 12, which will be due on that Sunday. So Sunday at midnight, I'm gonna desync the grade book altogether. So sync it one last time, then desync it. So anything you do after Sunday will not go towards your final grade. All right? Okay, all right, so where did we leave off? Okay, we were talking about metallic bonding. There's 4 different types of solids that we're discussing. So the first one is metallic bonding, you know, atoms composed of all metals. We looked at some different types here, our pure elemental metals, our alloys where we have a mixture of metals, and intermetallic compounds where it's like a molecular formula, but all metals are present. So I mentioned with metallic bonding, the idea that metals, they typically form cations due to their low ionization energy. So this translates into a sea of electrons type of model that you might have been, you know, just might have been described in high school. The sea of electron model is essentially adopting that low ionization energy, that the electrons, that one valence electron on silver is just weakly associated with those nuclei. So you can think of those electrons as delocalized. That's where the sea of electrons comes from. All of those valence electrons are shared amongst the whole bulk, you know, sample, metal sample. So that sea of electrons model can only explain some metallic properties like electrical conductivity. Electrons, because of that low ionization energy, can move around if there's an electrical bias placed upon that metal. Also malleability, where the nuclei can move past one another, that you're not breaking a like specific metallic bond here, that those atoms are just moving past one another. So that sea of electrons model does not explain some of the other properties we see regarding metals, and that includes melting points. when we go across a period. So I mentioned before in chapter 7, we talked about trends and melting points of metals going down a group. As our N value increases, we actually see melting points of metal decrease. So if we look at lithium and rubidium, lithium has a higher melting point because the radius is smaller. Metallic bonding typically occurs stronger when the atoms, metallic atoms are smaller. So that trend works really well going down a group, but doesn't work well going across a period. So we have to think about another trend here. So if we take our observations, we actually see across the D block, we see the melting points go up and then down. So the highest melting points are actually in the middle. These D5, D6 elements have the highest melting points. Cool, yeah, Fu said that would happen. So this idea of high melting points in the middle is directly related to band theory, which is basically the cousin of molecular orbital theory, where when we fill our atoms, we want to think, fill our atoms with electrons, or these metallic bonds with electrons. We want to think, are we putting those electrons in bonding orbitals to strengthen the metallic bond, or are we putting them in anti-bonding orbitals, essentially weakening the bond? So when thinking about metals, instead of discrete orbitals, molecular orbitals, since there's so many atoms in a metal sample, all of those molecular orbitals kind of get smeared, and that's where we get bands. So you might have heard of terms like valence band and conduction band when talking about conductors, even semiconductors. This is that same type of thing. So if you learn about band theory in like your material science classes, essentially it is based upon MO theory. So you're welcome. So the idea here is as we add more d electrons going across a period, we start filling our bottom half of our MO diagram, which is bonding, strengthening the metallic bond. That's why the melting point goes up. But once we get past, D5 elements, those additional electrons that we fill start going into anti-bonding orbitals, weakening our metallic bonds, and that's why our melting points start to go down. And so I wanted to show this picture here. This was from chapter 9, where we filled our molecular orbitals across our period 2 diatomic elements. We see the same thing here. If we wanted to calculate the bond order for boron, what would it be? What's the bond order there? How do we calculate bond order using MO diagrams? It's number of electrons in bonding minus anti-bonding over 2. So what's the bond order in diatomic boron? Whoops, yes, 1. What about diatomic carbon? 2. What about nitrogen? 3. So is the bond getting stronger or weaker as we go across the period? Stronger, okay, but then what happens when we go to oxygen? Those 2 added electrons are now going where? Anti-bonding. So now the bond order is 2. Then for fluorine, it's 1, and diatomic neon, it would be 0. So it doesn't actually exist. So we see the same thing here. Bond order strength goes up towards the middle of the period and then starts to go back down because we're adding electrons to anti-bonding orbitals. So we're not learning something new here. If you can associate this diagram with this one, then there's less to remember. All right, in that sense. All right, so that is metals. Okay, where are we? Okay, so metals. Typically with metals, we have a lot of atoms that are associated with one another. We usually have really efficient packing. Once we go towards more non-metallic elements, we start to form covalent bonds. So there's basically 2 thoughts. There's 2 different categories of how solids can incorporate covalent bonds in their structures. Either the covalent bonds can be in a network. This typically happens when there's a low number of valence electrons possible for an atom. So carbon, silicon, low number of valence electrons, these adopt network covalent solids versus nonmetals that have a greater number of valence electrons typically bond to themselves instead of extending into a network. So you see here this P4 molecule, each phosphorus only needs 3 bonds to complete its octet. And so what it's doing is just bonding to itself. Same thing with like sulfur. It just needs 2 bonds to complete its octet if you think about its Lewis structure. So it's just bonding to itself, making discrete molecules. So what I want you to kind of think about is in the solid form, molecular solids are held together by IMFs. We remember this from chapter 11, but this is different from network covalent solids because it's all covalent bonds are what hold those solids together. So which one are we going to look at first? Molecular solids, because we just talked about this in chapter 11. We have discrete molecules held together by IMFs in the solid phase. So we have, weak intermolecular forces. Sometimes we call these van der Waals forces that hold together the molecules from moving translationally, all right, from one another into a liquid. But the big idea here is that IMFs are weak. So when we are looking at a molecular solid, typically we're looking at all nonmetals in the chemical formula here. They have very low, relatively low melting points. We use the same IMFs trends from chapter 11, weight, if it's a nonpolar compound. We look for dipole-dipole interactions, or we look at hydrogen bonding, for example. But typically they have relatively low melting points, like you see here. Acetonitrile, its melting point is -46, so acetonitrile is a liquid at room temperature. Sucrose or sugar is a solid at room temperature, but it doesn't have that high of a melting point. 180 degrees Celsius, you could, melt that down on your stove if you wanted to. All right, so here we have a crystalline structure of H2O solid or ice. All right, that was a joke. Okay, all right, so let's look at the interactions in this crystal structure. If we were to melt ice or turn H2O solid into H2O liquid, what do we break? What do we break in this picture? Do we break this interaction right there? No, we break these interactions, all right? The ones that allow for translational motion, we're just breaking IMF. So we do not break covalent bonds. We're only breaking IMF. Specifically, we're just breaking some of the hydrogen bonds that hold together water, just some of them. Because when we turn a solid into a liquid, do we break all of the intermolecular forces? No, we don't. We would break all of the intermolecular forces if we would turn it into a gas. So when we turn a solid to a liquid, we just break some of them. All right, so those are molecular solids. Same trends that we talked about in chapter 11 when looking at boiling point. So just think about IMFs and its relationship with kinetic energy and the temperature at which something melts. All right. All right, so here's another example of a molecular solid. Graphite, so this is an allotrope of carbon, so only, pure carbon is in this sample, is another example of a molecular solid. So this crystal structure is also held together by weak intermolecular forces, van der Waals forces. So if we think about graphite and its purpose in our world, graphite is, well, not this pencil, but it is contained in like lead pencils. So it's funny, they call the inside of like pencils lead, but it's actually not like elemental lead, it's actually graphite, all carbon. And this is the crystal structure it adopts. So when you use I haven't used a pencil in years, I just use an iPad now. Welcome to the future. So when you use a pencil, I imagine, you draw across a page and you're depositing a small layer of carbon sheets. And so in the crystal structure, you can see how this comes about. That here, these covalent bonds, all right, like these bonds between carbon atoms, those are covalent bonds, all right? So when we actually use graphite lead or whatever in our pencils, we're not breaking those bonds, but we're breaking those dotted line bonds between, or the IMFs between the actual sheets. So those are weak interactions, enough where you just have some pressure, you know, on your pencil and paper is enough to deposit and break those IMFs there. All right. And so, you know, remember some of the properties of molecular solids, soft solids. So we know graphite lead in our pencils is rather soft as well. All right, so those are our molecular solids. So the things you want to look for when trying to identify molecular solids, nonmetals, discrete molecules, because if you have a discrete molecule, when you bring those molecules together in the solid phase, they're held together by intermolecular forces. So let's talk about the other substance that also has nonmetals. And that is covalent network solids. So these solids also contain nonmetals, but there are no discrete molecules. That's the difference here. So the most typical covalent network solid we talk about is diamond. So another allotrope of carbon, but there are no intermolecular forces holding the solid together. It's actually just covalent bonds. So covalent network solids only have covalent bonds. And so when we compare covalent bonds and IMFs, which one's stronger? Bonds or IMFs? Bonds, yeah, chemical bonds or covalent bonds, so much stronger. So we're gonna see that propagate in the properties that we see. We're gonna see really high melting points. We're gonna see really, you know, tough, hard materials here. So we're gonna see really high melting points. They're virtually insoluble in all solvents. They're typically insulating. If they're a semi-metal, then they may be semiconducting in nature. So here's some example. Diamond, which is just carbon atoms that are all covalently bonded to one another, has a huge melting point of 3,000, over 3,000 degrees Celsius. Silicon dioxide, do we know what the street name of that is? Glass, yes, it is glass. Yes, also has a very high melting point and is also classified as a covalent network solid because silicon is in the same group as carbon, but it's a semi-metal, and oxygen also is a non-metal as well. And because we can't, if you looked at the crystal structure of silicon dioxide, you would not find a discrete SiO2 molecule like you would water. You would see this extended network of silicons and oxygens. All right. So in diamond, each of those carbon atoms, why our melting point is so strong, if we looked at, this one's kind of hard to see, but if we looked at one of these carbon atoms and counted how many electron domains were around one carbon atom, we would see that there's 4 electron domains around each carbon. So what is the hybridization of a carbon with 4 electron domains? sp3, yeah, and so we have these sp3 tetrahedrals all stacked together, ordered very nicely, and that's what gives diamond its really, really tough properties and high melting points. It takes a lot of energy because each carbon is bonded to 4 other carbons, which are then bonded to 4 other carbons. That's why it's so hard to just break a bond and why diamond is so tough. All right, so I almost get to rant about diamonds. Just need to talk about ionic solids now. All right, so covalent network solids, oftentimes mistaken for molecular, but we see they have very, very different properties. They're sometimes mistaken because there's nonmetals present. Ionic solids, on the other hand, sometimes have similar properties to covalent network solids because they typically have really high melting points, and they're somewhat tough, they can be brittle, but their composition is super different, all right? The other two, all nonmetals, these ionic network or ionic solids, you know, remember our naming rules. Ionic solids always have a cation and an anion, or even more simply, a metal and a nonmetal. So that's what you want to be looking for. Ionic solids, they're held together by electrostatic attractions. You have to have ions, a cation and an anion, for the electrostatic attraction. We typically see that with a metal and a nonmetal. So high melting points. So the neat thing, and I mentioned this before, ionic solids like sodium chloride solid is actually an insulator. If you put probes on, a piece of rock salt and tried to check for its electrical conductivity, there would be none. But as soon as you dissolve salt in water, or any ionic solid in water, that's when it conducts electricity. So it has to be, in order to conduct electricity, you need to have free ions. And so in the solid phase, ionic solids cannot conduct electricity because those ions are fixed into place. But as soon as you dissolve it, it does conduct electricity. All right, so ionic solids is where a lot of our pretty gemstones come from. So a lot of different gemstones that we interact with, ruby, sapphire, they all come from the ionic solid aluminum oxide. Basically, the different colors we get are just different impurities inside the crystal structure of aluminum oxide in the ionic solid, which is pretty cool. So like, for example, ruby, what we understand as red, has a little bit of chromium contamination inside the structure. And then blue sapphire, there's actually different types of sapphires, has a little bit of iron and titanium. So we know ionic solids, or these gemstones, we like gemstones because of the color. We like them because they typically are very tough, and they last a long time. So don't relate that to the idea that, oh, NaCl, salt always is very soluble in water. Not all ionic solids are soluble in water, and we actually know that from our solubility table as well. Aluminum oxide does not dissolve in water, but sodium chloride does. So the idea here is not all ionic compounds are soluble in water, but if they are, they'll be strong electrolytes. Okay, so those are ionic solids. We've already talked about those. Okay, so why does Dr. Wynn hate diamonds? So hopefully the De Beers company doesn't cancel me. All right. So I want to talk to you about gemstones because I'm just I just have a stupid monkey brain and I like shiny things, okay? And so I don't personally like to buy diamonds, and I'll show you why from a chemist's point of view, and because I'm cheap, right? I've mentioned before that I'm fairly cheap. So let's think about this. Diamond, all right, very shiny, sparkly, it's carbon, right? This is a covalent network solid. We already talked about that, covalent network solid, all right? It has a high melting point because of that, and it has a Mohs hardness of 10. That's just the scale. They define diamond as 10. So me personally, I avoid diamonds, and if I'm going to buy a gemstone, I'll choose moissanite. So moissanite is actually compositionally 50% carbon, 50% silicon. So if we look at this chemical formula, what type of bonding do you think we'll see? Do you think it'll be ionic? Do you think it'll be covalent network? Well, let's eliminate some. Is it metallic bonding in silicon and carbon? No, because those are nonmetals. What about ionic? No, there are no ions present. So our last two is molecular and covalent network. So which one do we think it is? The network one. It's going to be covalent network. Let's just think about it. Carbon is a nonmetals in group 4A. We're just replacing half of the atoms in diamond with a silicon atom instead. Silicon is actually in the same group as carbon, all right? So, we're just replacing half of the atoms, and we're just replacing it with its big brother, all right? So moissanite is actually also a covalent network solid. So that's the gemstone I typically go with. It also has a fairly high melting point and a really high hardness as well. So let's look at the last kind of diamond alternative here, and that's cubic zirconia, all right? Based upon that structure, or the composition, what kind of bonding are we looking at? Solid bonding. Is it metallic? No. Is it, well, what is it? Zirconium is what? Okay, I will give you, it's number 40. It's a metal, and oxygen's a non-metal, so what kind of bonding is that? Ionic, yes. So cubic zirconia is ionic bonding. It still has a fairly high melting point and a pretty high hardness as well. So for me, from a chemist point of view, where I understand composition and structure, dictates chemical properties. If I'm going to look at a diamond alternative, I want to pick the one that is, you know, by composition most close to diamond. And so to me, that's going to be moissanite because only half of those atoms are silicon and we still fall under the covalent network solid bonding regime versus our cubic zirconia is ionic. So that's kind of like a different class that you see here. So that's looking at the composition and identifying, okay, what kind of bonding is occurring here. Let's look at the structure. These are the crystal or the unit cells of the different, our different things. So here's diamond, it adopts a cubic unit cell. So let's, what is the hybridization of this carbon atom right there? So remember, this is a throwback to chapter 9. Hybridization, what do we count? Electron domain. So we're essentially just counting bonds. So how many bonds are around that carbon atom? 4. So what's its hybridization? sp3. Okay. That's diamond. It's cubic. Moissanite, so still network covalent bonds. It has a hexagonal unit cell. Let's determine the hybridization of this gray atom. Let's pick one that you can see all the bonds. This one, that one. How many bonds on to that gray atom? 4. So what's its hybridization? sp3. Ooh. De Beers, I'm coming for you. The hybridization of the red atom in cubic zirconia. So this one is a cubic unit cell. So this guy, how many bonds to it? 4. So what's its hybridization? sp3. Wow. All of these diamond alternatives have sp3 structures, okay? And that tells us a little bit about, you know, why all of these look all similar. So here is the different gemstones. Can you tell them apart? No. Yes? Which one do you think is diamond? The first one, they are in alphabetical order. So it's gonna go cubic, diamond, moissanite. Wow, yeah. So me personally, I will purchase, so like my wedding rings and stuff, I picked these out myself and I chose deliberately moissanite because of the mixture of carbon and silicon. It still stays within that network covalent realm. Structurally, it's similar and compositionally, it's similar. And it's a heck of a lot cheaper. But you know I'm cheap, but I'm not so cheap that I'm gonna buy cubic zirconia, because recognize that, you know, you're gonna put a gemstone into a setting, and that setting is typically in gold. So if you're gonna put something super cheap in there, you'll probably have a cheap setting as well. So I wanted something kind of middle of the road. I wanted most of, you know, the money to go towards the actual artisan and not, you know, the gemstone. So that's me personally why I don't buy diamonds. Yeah. Yeah, the diamond looks a little bit yellow because of impurities, yeah. And so you can even find like black diamonds, brown diamonds, and because of the impurities. And we'll see in the next slide, I think, when I talk about my wedding ring and why it's interesting. So just wait, yes. What if they got scammed? Yeah, I don't know. I couldn't help them. But if I think like jewelers and stuff, they have tests and things that like test for diamonds and. Yeah, I don't know. But it probably measures some type of conductivity, or actually no, I think it measures refractive index. Yeah, and so like to me, I don't see a freaking difference between D and like any of them. So like to like the naked eye, do you think that this is not diamond? Or does your monkey brain just think it's shiny? It's shiny, yeah, and so I'm happy with that. I'm happy with that. But talk that over with your partner of choice, because that's a personal decision, all right? So my decision was I'm gonna pick out what I want, and I just put it in my husband's cart. Okay. All right, so I mentioned So gemstones, alexandrite. So my wedding ring, I don't like to be normal. So one, I'm not going to buy diamond. I'll buy moissanite. But my the gemstone, the solitaire in the middle is actually alexandrite, which is a unique gemstone because I'm a unique person. They call it emerald by day, ruby by night. It actually changes colors depending on what the white light composition is. Yes, I was a mood ring girl when I was in grade school. But I want to show you that this has to do with chapter 6 stuff, all right? So yes, it's emerald by day, ruby by night, and the reasoning is because of we have some chromium impurities basically swapping out with aluminum. We get 2 absorption bands in its absorption spectrum. It absorbs blue light and yellow light. So what you see, depending on the white light that comes in, depending on the composition, if there's a lot of blue present, you'll essentially get the mixture of red and blue being reflected to our eyes, so it'll look something like purple. Or if you're by red light, like incandescent light, candle light, where the composition of that light is warmer, there's a lot of reds in it, the gemstone will reflect mostly red because of the dual absorption bands. Yes, so here is chapter 6 review. So here are the 2 absorption bands of alexandrite, A and B, and you can see here the wavelengths. All right, so I have 4 different transitions here. So remember where absorption bands come from. Electrons are absorbed, or sorry, light is absorbed when electrons do what? When they fall or when they jump? Jump, yes. So which of these transitions translates to which absorption band? Okay, which ones can we eliminate off the bat? 1, 2, 3, or 4? Yeah, we can eliminate 2 and 4. Why? Yeah, it's going down. So in those transitions, 2 and 4, is light being absorbed? No, light's being emitted. So you would see something like fluorescence for those different transitions. So we're looking at 1 and 2, or sorry, 1 and 3. So how does 1 and 3 differ? Their energies, yeah, okay, but is this graph in energy? No, it's not, it's in wavelength. So we need to ask ourselves, okay, 1 is high energy, so how does that translate to wavelength? Short, yeah, so as E increases, wavelength decreases, frequency increases. So A is which transition, 1 or 3? 1, yes, that's A, and then 3 is B, yay! There's my ring. I picked it. Okay, cool? All right. So there we go. So there's alexandrite. I think it's pretty cool. And so here's some more gemstones, all right? So we looked at gemstones that are ionic. So alexandrite is an example of an ionic gemstone because there's, what is it? There's like beryllium, aluminum, oxygen, and chromium, all right? So this is more of an ionic type of a structure. Diamond and moissanite were more our covalent network solids. So, you know, from this list, don't even read the list. Do you think you would expect any molecular solids in this gemstone list? Molecular solids. No, because molecular solids are soft. Do we want our gemstones to be soft? No, we want them to last forever. You know, like the idea that diamonds are forever, but they're not, remember? Because are there heats of formation of carbon solid diamond? It is not 0, it's carbon solid graphite is 0, yes, okay. So yes, we're not gonna find any molecular solids on this list. If you look really carefully, most of them you'll see are actually gonna be ionic. Look, pearl is calcium carbonate. We know how to name that. And some other ones here, some silicon dioxide ones. Those are covalent network. Garnet is this magnesium aluminum silicate substance. So a lot of ionic gemstones in here as well. All right, so we're not going to find any molecular. All right, so I like pretty colors. And so from what you see, a lot of the pretty colors come from ionic substances that have metals in them. And that's why I like inorganic chemistry, because that's where the pretty colors come from. All right, so that's my rant. So rant over. So now let's kind of cap off some of the properties that we can look at for the remaining solids here. All right, but I'll show you here that there's nothing new that we're actually learning here. So we can actually trend the melting points of ionic solids. All right, we know ionic solids have fairly high melting points, but it's based upon something you already know, lattice energy. The greater the lattice energy of the ionic solid, the higher the melting point. So you already know the trends there. So for lattice energy, we look at Q1, Q2 product, and then if those match, then we look at size. So yeah, the idea here is that our lattice energy increases with increasing melting point temperature, and it's proportional to the Q1, Q2 over D. So we're not learning something new. Good? Yes. All right, so let's just do, so larger lattice energy, higher melting point. All right, so let's look at these examples. We have NaF, NaCl, MgO. Based upon these melting points, which substance has the highest lattice energy based upon the melting points? MgO, yeah, it's going to have the highest lattice energy. Because remember, lattice energy is what's keeping your ions together. And in order to melt something, you are essentially giving it enough kinetic energy for those ions to, form the liquid form and move past one another. So you're essentially breaking your lattice energy. So higher temperature required to break a higher magnitude of lattice energy. Yes, okay, so it's going to be MgO. All right, so let's increase these three substances in order of increasing melting point. So really, what is this question asking? Order in increasing lattice energy. Yeah, so we're not learning something new. So we first look at Q1, Q2. So MgS plus 2 minus 2, plus 2 minus 2, and MgL is plus 2 minus 1. So do we know the lowest lattice energy or lowest melting point? Yeah, MgCl2, yeah. And so the last two, it's going to be these two. I just don't know the order. So what criteria do we look at next? Size, radii. So which of them will have the higher lattice energy? The ones that are smaller, yeah. So I guess the only difference here is sulfur and oxygen. So how is that different? Oxygen smaller, so it's not going to have the lower melting point. It's actually going to have the higher melting point, which is weird. But that's because the ions are closer, so it takes more energy, higher temperature to rip them apart. Yes, there we go. Whoops, there we go. Good, so we did not learn something new. Yay. Yay. You just have to associate lattice energy with melting point now. Also being able to identify what a ionic solid is, when to invoke, lattice energy. Because what if I had a question like this? What if I had like, okay, NaCl, CH4, and CF4. Which one has the lowest melting point? Which one has the lowest melting point? Are they all ionic? No, they're not. So you need to now conjure up what are some of the trends of molecular, all right, because the other two substances are molecular substances. So we don't use lattice energy there, all right? Or let's think about this. CH4, what is that? That's methane, yeah. Is methane a solid at room temperature and pressure? No, it's a gas. So that means its melting point is real freaking low, because what's keeping it together in the solid phase? Pretend that it was a solid. What's keeping it together? IMF. So that's actually going to have the lowest melting point. Actually, so both of these. So CH4 and CF4, they're both nonpolar compounds. Of these, both of them are technically molecular solids. IMFs are holding them together. Which one has the weakest IMFs present? Methane. Why? It's lighter, yes. Yeah, CF4 looks the exact same. It's just a lot heavier. So it's going to have more IMF. So it's going to be CH4, then CF4, then NaCl. Yes. Okay. All right. So I tricked you. I'm sorry. In this example, I wanted you to recognize, oh, we have molecular compounds that typically have lower melting points because of those weak IMFs, comparing that to ionic solids, which have higher IMFs. Then I could throw in something like magnesium oxide in there as well, and that would be the highest, where we would have, moleculars, you compare IMFs, ionics, you compare lattice energy. Yes, all right. Okay, cool. All right. So structuring ionic solids. So remember, when we melt stuff, we're separating those charges, but thinking about how the charges exist in 3 dimensions. We have cations and anions coming together, all right? Cations and anions, they're attracted to one another. But when we bring together those cation and anions, we're also bringing together cations and cations together, anions and anions together. So when we form an ionic compound, we want to make sure we maximize all of the attractions between oppositely charged particles that are in that structure. But we also want to minimize any repulsions between, 2 anions or 2 cations. All right. So based upon our ideas from chapter 7, our trends, our size, our atom sizes, remember, these are ionic solids. We have a cation and an anion present. So here's some structures. So we have a purple particle and a yellow particle. That purple particle, is it more likely to be a cation or an anion? The purple particle. But you just said cation. You changed your mind. So the purple particle is most likely going to be an anion. Anion is negatively charged. So do we see why the purple particle, because it's bigger, anions are always bigger than their neutral atom. So the purple particle is most likely going to be the anion, the negative one. Now do you see the yellow one? All right, is most likely going to be the cation, because when we form a cation, what are we doing? We are removing an electron, so our atom always gets smaller. So that's why the yellow particle is the cation. Okay, so keep that in mind. Purple particle is the anions, all right? And the yellow particle is the cation. Which structure is more stable? The left one or the right one? The right one? I looked at this and I'm like, the left one looks prettier. I don't know, it just looks prettier to me. But remember why ionic compounds form the way they do. We want to maximize attractions and minimize repulsions. So look for the picture that does that. Yeah, so what's the problem with the one that I initially thought, the one on the left? Yeah, those negative anions, they're touching one another. So there's really high repulsion there. We have high repulsion. We do have attractions there, but basically those repulsions cancel it out. Versus the one on the right, which is the correct one, it's the more stable one, we still maximize our attractions. We have 4 anions touching that one cation, but we're minimizing the repulsion between the anions around it. So this is the structure that is the most stable. So remember when we looked at unit cells and like why atoms pack the way they do? This is why they pack the way they do, because we need to minimize repulsions and maximize attractions within our unit cells. So we get all of those different funky structures. So ionic packing, what type of packing structure that we see is dictated by the difference in sizes of the cations and anions. This is dictated by the radius ratio rho, where we take the radius of the cation over the radius of the anion. And because the cation is typically smaller, rho is usually less than 1. It's usually less than 1. Is that? Yes. Yeah, it's usually less than 1 because the cation is usually small, or the cation's usually smaller. All right, so the radius ratio, that rho value, will allow us to predict some of the structures and coordination number and the efficiency of packing that we see. So coordination number is a way we can inspect ionic structure. Coordination number is really similar to how we determined hybridization. We look at an atom and we count how many electron domains are around it. That's basically what coordination number is. You look at one atom and you count, okay, how many other oppositely charged particles are bonded to it. So for example, you look at that cesium, how many other chlorines are like touching it? 8. Yeah, so cesium's coordination number would be 8 here, all right? So here is actually a bunch of different structures for ionic compounds, and we see the radius ratio. Rho is decreasing left to right. That the most, the row that's closest to 1 here, we have really high coordination numbers, 8 and 8 for cesium, 8 for chlorine. But if we go to something like sodium chloride, where its radius ratio is here, all right, it's 0.7. It's their coordination numbers of the sodium and chlorine atoms, or ions, sorry, are 6 and 6. And then when the radius ratio is around like a half, all right, so the anion is twice the size of the cation, we see the less efficient packing. The cation anion coordination numbers are 4 and 4, so it decreases that way. So we see as our radius ratio approaches 1, we actually see the coordination numbers increase. We have better ion packing. So highest coordination numbers are seen when we have ions that are similar sizes. That will give us a radius ratio of 1 in that case. So in all of these examples, the cation anion ratio is 1 to 1. So here's cesium chloride, sodium chloride, and then zinc sulfide. It's all 1 to 1. So we see the coordination numbers match one another. We see the coordination number of the cation, that there's 8 anions around each cation. Each anion has 8 cations around it. So we see the ratio match. But if we had something like calcium chloride, all right, if we were looking, if I said that the cation coordination number was, let's say, 8, meaning that if we were looking at a cation, there's 8 anions around it. If the formula we're looking at is calcium chloride, then what would the anion coordination number be? Would it also be 8 based upon this formula? Would it also be 8? Let me ask you, if you were to look and compare at the number of particles of calcium versus chlorines, should there be twice as many chlorines present in the actual crystal structure? So if the coordination number of around each calcium is 8, that means each anion will have a coordination number of 4, that there's only going to be half the number of cations around your anion. So we see in the coordination numbers is reflected by your empirical formula as well. I just needed to show an example because I think there's a homework problem about that, and all of these are just 1-to-1 ratios. All right. So you'll see coordination numbers will be reflected in your formula. Your coordination numbers are reflected in your formulas as well. All right. So let's get on to the very last learning objective for this chapter, and that is determining formula units from your unit cell. All right. Because if you look at this picture, all right, for this unit cell, for cesium chloride, you might quickly look at this and be like, oh, how did I get 1 chloride, 1 cesium? There's 8 chlorines present in that unit cell. So we need to think about where on the unit cell are those chlorine atoms. So we need to be cognizant. We have these perfect squares. Where are the atoms placed on that unit cell? If you have an atom that's completely inside the unit cell, then we can say, yes, we have a full atom inside that unit cell. But if an atom is on the face of a unit cell, all right, that only half of that atom is inside one unit cell, and the other half of that atom is inside another unit cell. So when we're trying to count up, okay, how many atoms are present in one unit cell, we need to be cognizant of where it is. So like this is kind of clear, like this atom is on the face of this unit cell, but only half of it is actually inside the unit cell we're focusing on. So yeah, if it's on the face, count half an atom. If an atom is on the edge of a unit cell, only count a quarter of the atom, because basically that atom is sitting on point where there's 4 unit cells all coming together. So you only count half of it because we're just focusing on 1 unit cell. And then finally, if an atom is on the corner of a unit cell, you only count an eighth of an atom. And so we just need to take inventory of how many total atoms are inside 1 unit cell. So here's a common question. We'll take into account where the atom is. So here are 2 ways to represent copper. Here's one way where you can clearly see like where the atoms are relative to the unit cell. And then here you can see it kind of spliced and see how much of the atom is actually inside the unit cell. How many copper atoms are in 1 unit cell? So let's zoom in here. I like to just take it like section by section. So I'll look at this corner. I'll see, okay, there's a carbon or a copper atom in that corner, but there are other copper atoms that are identical to it. There's 1, 2, 3, 4, 5, 6, 7, 8 atoms in the corner. So when it's in the corner, how much of the atom do we count? An eighth, yes. So total, how many atoms are coming from corners? Just 1, yeah, 1 atom. All right, but I didn't take into account all of the atoms. So where is this atom, the pink one? That's on a face. So 1, 2, 3, 4, 5, 6. So 6 atoms on a face. Does that make sense? A dice has how many faces? 6, yeah. So we have 6 on a face. How much do we count from a face? A half. So there's 3 copper atoms coming from faces. So there's a total of 4 copper atoms total inside that unit cell. Right? So that can tell us something about the packing efficiency and so forth. Yes, there's the answer. Perfect. So in this example, we did, it's just the same atom. I like these. They're like fun little puzzles. You just have to see where are the atoms. All right, so let's do some more. All right, let's determine what is the empirical formula for these compounds in this unit cell and also answer how many formula units are inside this unit cell. We're essentially doing the exact same thing. We just need to be cognizant of, okay, what atom is where. So let's look at this compound. You might just look at this and think, oh, that's CSCl8. Does that look right? Have we ever encountered something like that? No, we need to actually think about where are those chlorine atoms. So that is not correct. So let's do the easy one first. That's cesium. Where is it? It's in the inside. So how much do we count of it? Just the whole thing. So there's 1 cesium atom there. All right, the chlorines. So let's focus on the chlorines. They are where? Corners. And how many are there? 8. So we have 8 chlorines on the corner. So we count 1/8. So how many total chlorines are there? 1 chlorine. So can we see what the empirical formula is? Yeah, so we do the atom ratio thing, right? So this would be CSCl, that's it. All right, and so we did the empirical formula. Now how many formula units are inside that unit cell? Just 1, just 1. I'll show you the next example where it's not 1. Let's just do the next one. Okay. Let's call these red and purple. Which one do you want to do first, red or purple? Purple, yes, okay, purple. Where are those purples? They're inside, yes, they're inside. How many? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 purple inside, so there's 8 purples. Okay, all right. Now we do the reds. Reds, okay. So we have a bunch of reds on the corner. How many on the corner? 8, yeah, 1, 2, 3, 4, 5, 6, 7, 8. So 8 on the corner. When we do a corner, we count how much of it? An eighth. So how many total reds are coming from corners? 1. But we didn't account for all of them yet. We still have to do the ones on the faces. So 1, 2, 3, 4, 5, 6. There are 6 coming from faces. So how much do we count on a face? Of half. So there's 3 R's, red atoms coming from there. So total, there are 4 red atoms and 8 purple atoms. So can we get the empirical formula here? You might just write, okay, P8R4, but is that an empirical formula? No, what do we divide by here? The common denominator, and that is what? 4. Yeah, we're dividing by 4 here. So we see that the formula is actually P2R, right? Two purples for 1 R. So this would be our empirical formula, empirical. So then how many formula units are inside 1 unit cell? In this case, it would be 4. So we use the multiplier. The multiplier is what tells us how many are in there. All right. Okay, so I wrote the formula backwards, but whatever, they're just colors. So let's do the last one. Okay. And this is where I clown my boss, or your book author. All right. So here's a unit cell of a perovskite. So here we have calcium, all right, titanium, and the gray one is, the red one is oxygen. So it's the same thing. How many calciums, titaniums, and oxygens are there? So let's do the first one. Calcium, which is blue. Just 1, yeah. There's just 1 calcium because it's on the inside. Titanium, they're all on the corner. They're the gray ones. So there's 8 of them times an 8th. So there's 1 titanium as well. And then finally, the red ones, those are our oxygens. Carefully count how many there are. Red atoms. 12. And they are on what? The edge, not the face. They're on the edge. Yeah, so on an edge, how much do we count? A 4th, yeah. Because you can think 4 unit cells come together to make one of those edges. So there are 3 oxygens. So what is the empirical formula? CaTiO3. Perfect. Aren't these fun? They're fun. And then how many formula units are inside the unit cell? Just 1, yeah, because that is the empirical formula, all right? And so I'm joking, I'm not clowning my boss. Patrick Woodward, who's one of our textbook authors, he is the leading expert on perovskites. The old edition of the book had perovskites all over the front because he's an author and he can do stuff like that. And here's his faculty picture. He's literally holding a perovskite. But I think that's pretty cool if you're so, genuinely interested and passionate about it. Then write a book about it. All right. So on Wednesday, we'll do review. Homework's due on Sunday. Everything is due on Sunday.